Okay,
That crooked. Or that crooked.
where? Okay, so what were we doing? Oh, hold on, check this out. We're almost to this week 11, lecture 2. Okay, look where we're supposed to be. Okay, what's today?
16.
So we're only 2 weeks behind. We're almost there, guys. We're almost caught up. Wait, where's my mouse? Okay. So we're close to the end. Thankfully, I put in some extra weeks at the end to catch up. I didn't use them last time because we mostly did coding at that point, but this is all going to kind of move down. So we started on this idea of gravity waves, okay? Now we're going to talk about waves on a density interface, internal waves, and then you'll notice here in the reading, we're going to go back to chapters 4 and 5 to talk about rotation. So far we've talked about pressure waves and surface tension, gravity as a restoring force. Where we're headed is the idea of adding more terms to the Navier-Stokes equation. So I know how we were like, well, we just fucking understood the Navier-Stokes equation. Why are you adding more terms? Well, that's how life is. That's how life do, Okay. And then once we have velocity in a rotating frame, then we can do geophysical flow. So these are planetary scale, planetary size waves. And then we can look at this idea of laminar flow. And we can begin to talk about things like turbulence. What does turbulence mean? In order to talk about turbulence, you have to talk about turbulence isn't. That's laminar flows. We may or may not get to similarity solutions. I think it's really important to do boundary layers. We've kind of alluded to them for a long time. How does the fluid act right at the surface of something else? So what is the interface with something like the air on this table? That's boundary layers. Actin layers, I mean, you basically could do this at the same time that you do geostrophic flows. These and all these different types of internal waves, we can decide whether or not we have time for them, whether we care about them. These are all different types of waves that you find in geophysical applications. And then instability. So if we get to the end of class and we want to get rid of this week, I think we could have instability in the conversation with laminar flow. But I would really love to kind of move quickly through this to get the boundary layer. I think that's a really important topic because if you care about aerodynamics, if you care about how it is that we design objects to flow through fluids, you have to understand boundary layers. And then they're also helpful because the mathematics is associated with the same type of mathematics that you would do boundary layer and boundary conditions are the same types of math that we use in other applications. So if you're not thinking just about computational, but you're thinking about where can I use this, then that's an important place. Okay, so here's where we were. Everybody can see that, okay, right? All right. So what were we talking about? Anyone recall?
Streamlines. How about how parcel fluid moves and the different types of examples?
Yeah. And I said that I wasn't going to do the solution for you, but if you look on page, okay, on 8.37, equation 8.37 describes the streamlines. And from this, you can get things like the path lines and the street lines. And so you can see how a single particle moves. So this is the deep water approximation. What does it mean for the water to be deep in this context?
It's deeper than it is like wider.
Close, what do we mean by wider?
Like
Wavelength, right? Good. All right, so what are we saying here? We're saying lambda is
portion, almost,
It looks almost the same, but it's not supposed to,
so it's less.
less. Okay, and what's this one? Almost the same. And this one? You'll notice here, this is a double small. This is only small. Okay. We also showed something about a dispersion relation. What does a dispersion relationship mean?
Relationship between. The wave number and the frequency.
Right. So a dispersion relationship takes omega as a function of k. And sometimes we write that in terms of c. How do I write c in terms of omega and k? No, just omega and k only.
Omega over K.
Omega over k, right? So in fact, if I can find any solution of omega k, then I just divide by k and I get a relationship for c. C being the phase speed. Okay? This is the phase speed of the wave. This is not the sound speed. So currently I'm talking to you, right? And there is maximum speed that air can send information, right? That is not necessarily the wave speed, the phase speed of an object that I launch in the air, right? So for example, I'm speaking right now. That may be a different wave speed than if I move my hand and it creates a perturbation of air that travels towards you. Why is that the case? How is that physically possible that different waves could travel at different speeds?
Because some waves are bigger and smaller than others.
Good. Some waves are bigger and smaller than others. And we saw earlier that the wave speed depends strictly on wavelength, right? Okay. So as we make perturbations, some of them are going to move faster and some of them are going to move shorter. Slower. Okay? Okay? Everyone's happy? Okay. So let's write this then for the general form. So C for this was G over K inch KH. You guys okay with me writing inch like this? Okay. So let's do the approximations here. And then we'll just move directly into some other forms of these waves so we can understand them better. For deep water. Okay. H is much, much bigger than lambda. Right? So what does KH look like? Right? So H over lambda is bigger or smaller than one here? Bigger one. So H over lambda is bigger than 1. Okay. So for the deep approximation, inch of x approximately equal to 1 when x is much bigger than 1. The shallow approximation, branch of x, approximately the x is. Okay. So we can see, of course, this would be the opposite version here. Lambda is less than 1. And now we can write what this is for each of them. Right? So if this thing is 1, in the deep case, c equals the square root of g lambda over 2 pi. And if this is x, well, then the 2 pi's cancel, the lambdas cancel, and it's just gh. Cool beans. Okay, so what did I say? What can we interpret from these two? We started off by saying this is like ripples in a pond. Right? Small perturbations, they're small compared to how deep the pond is, right? Some glassy liquid pond. Whereas this one here, these might be like perturbations in a stream, maybe a thin bed, someone steps on it, right? Or it's going around some flow in the rock, creating some waves, right? Here, what we see is that the speed is wavelength dependent. Longer wavelengths, higher speeds. Okay. Can you go infinitely long here? I mean, wavelengths can keep going up and up and up, right? So there will be eventually a problem, right? Speeds can't reach speed of light. But we run out of that issue once we move away from the idea of what it is. So what I mean by that is that we have this Knudsen approximation that we started with, which says that we need a certain number of particles in a certain distance in a certain region to bump into each other frequently enough that we can consider it a fluid. Wavelengths that get too long, that no longer applies. Right? To take any geophysical object like the Earth or even like a star, you can have these on there. They still won't be infinitely long. Okay, and this one here? This one says everything's happening at the same speed. In shallow water, all the waves are moving at the same speed. Okay. Cash money? Okay. We're not gonna talk about this. Also, don't know if we're gonna talk about this. What? Why? Because we don't have time and I don't know if it matters to us. Let me just show you the picture. Because this would be the issue of wave refraction or reflection. And one thing that we really want to think about, we use these approximations to kind of generally talk about waves. And the thing that's really nice about mathematics is that if you can express them in one form in a certain context, and you see that, let's say this variable h divided by lambda, we see that there's different regimes, right? So they're not distinct. It's not like you have one, then the phenomenon turns off and it becomes a different thing, right? They smoothly transition from one to the other. And so in some ways, we can use the same mathematics to describe places that maybe are right at the edge of our approximation, okay? So you might have something like this, where you have a deep part when you're very high up, and you're comparing it to sort of more shallow waves, internal waves. And one thing that is happening here is we can think about the ways in which they bend, in which like wave fronts, right, begin to pile up. Okay. So this would be like the transition from deep water into shallow water, and the way that you can get refraction, that is to say, waves are going to bend when you move from one medium into another. Where have you seen this before? Light. Yeah, exactly. Straw. So water waves do that. And the mathematics is there for this, even in this medium that we have, right, which doesn't look like light, doesn't look like Snell's law, but the mathematics comes from this, right? And this is, I think, the more typical example. Okay, you have some cylinder in the center. This is a hard object. You can think of it as a rock in your stream. You can think of it as whatever you want. Okay, and you have wave fronts that are starting in this direction. Okay. Now, one thing I want you to see here. Okay, here's the wavefront. 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 Right, that is all the way over. Here's the paradox. Okay. How does the wavefront begin to bend before it interacts with the object? Because this is no longer straight, is it? Why does the wavefront, so this one is almost straight, like maybe if you believe my drawing, it's straight. But this one's not, this one's curved over. So is this drawn improperly, or is something else going on here? Because it hasn't touched the object.
That thing is pushing water,
What do you mean that thing is pushing water?
because the fluid as a whole, I think, it's pushing the particles in front of it to causing the other ones.
So like something related to surface tension of objects.
Yeah, we're gonna imagine that right now we're deep inside the water, right? So this could be even a submerged rock. Right, so like we're gonna think just in 2D here. What did you say?
Like it's causing a pileup, because like it's, like if it were just straight, it would just bounce back, but since it's like a sphere, it's like shooting off in different directions, but like backwards a little bit.
Okay, and that's kind of what you're saying? Okay, yeah. So what I would say is I would say that the fluid communicates that there's a boundary. Right? What I'm essentially saying is as I go in, right, and you're thinking about the microphysics here, it's talking to its nearest neighbors, and they're all bumping into something ahead of time, and therefore sending that information backwards, right, in the form of more pressure or more, right, resistance to the motion in this region compared to this region. Right? We'll see how the coming down is there. So it's slowing the fluid. Whereas this one's saying, whatever.
How's that a paradox though? I feel like that just happened.
I mean, you know that that happens. But if you don't have that explanation ahead of time, it's paradoxical. Remember that all paradoxes are just you not having enough information yet. Right? Oh, okay. So the paradox. The paradoxes of paradoxes is that the definition of a paradox is an apparent issue with the laws of physics, which is used as a teaching tool, and when resolved, demonstrates misconceptions about the physics. So you've heard about the time traveler's paradox, right? Or one of them, like, or the twin paradox, one of them goes away from Earth and comes back. And the question is, if they're moving relativistically, which one of the two twins should have aged? Oh no, we can't tell the difference. What's the resolution of that paradox?
Run the experiment.
Nope.
Do the time thing.
In order for the one twin to come back, he needs to turn around. And in the process of turning around, he is no longer in an inertial reference frame, and therefore he breaks the symmetry, and therefore he ages. Right? So there's always a piece of the puzzle that presents to you this simple thought experiment. Here, you do the thought experiment, and it's designed to trick you. It's designed to bring out something that looks unusual until you think about it just 20 seconds more. You're like, ah, I got it. Right?
So I like that thing you showed us in computational.
With what?
That one. When you showed us the plane and the bullets in the plane,
Bullets in a plane?
you showed us the computation, you're like,
Oh.
where should you put the thing?
Oh, yeah. That's a survivorship bias. That's, yeah, I don't know if that's a paradox. Paradoxes tend to be like they exist in science. Right? And so like people even talk about them. So we have them, like especially in this time period in physics, you have these things, people will be like, I don't know how to resolve this. And then they write papers, and someone comes along and says, oh, I got it. Right? And it leads to a breakthrough in science. So there's something called the ultraviolet catastrophe, which is the recognition. You heard about this one? So this is the recognition that if you have an oven and you use Maxwell's equations and Kelvin Maxwell's equations for how light works, then every oven should radiate an infinite amount of energy. And obviously ovens don't do that. And the resolution to that paradox was to quantize the energy. Now that was an observational result. That was required by observation. Right? Someone didn't just sit down and be like, I think we should quantize shit. It's like, this is the only way that the math works. Okay? Sorry, tangent. You should let me talk. As soon as I start talking, go on fucking tangents. Okay. This is called refraction. And so this is what happens in water. The water is a continuous media. We haven't yet talked about what happens right here at the boundary, but that really doesn't matter for these wave refractions. It's pretty common. I don't need to convince you that this happens, right? Oh, yeah, you do?
No, I mean like.
Okay. I was like, shit. Okay. So this is a really fun panel that really talks about. So this is pressure. So when you think about an atmosphere, you tend to think about it in terms of height. But some modelers and some meteorologists prefer to think about it in terms of pressure scales. So at the bottom is the highest pressure, obviously due to the column of air that's above it. So as I head up, things will happen at specific pressures, not altitudes. And what that means is that if it's hotter on a given day and the pressure is lower, then maybe one of these phenomena can move down, right? Or it can move up, corresponding, depending on what's happening. And here's temperature. So this is an overgeneralized version of our atmosphere. One thing that's happening here, 0 is like what we think of as freezing at surface, but that's not always the case because the pressure is dropping. So we can get water ice clouds, we can get condensation at different temperatures. The dew point here, you know what the dew point is? So this is like the condensation temperature as opposed to the true temperature. So what happens is at this point here, the water temperature drops low enough that you condense. Now you'll notice here that the dew point continues to fall and the temperature doesn't follow it. So this is why there can be a block in between what we consider cirrus clouds, which are high altitude clouds, and what am I trying to say? Cumulus clouds, right? So cumulus clouds are the big fluffy ones, the ones that look like they're gonna rain on you. Cirrus clouds, they're wispy. These are icy. They happen way up here. Totally different pressure regime, and there's a hole in between them. Okay. When you fly on a plane, you go, you punch through the cumulus clouds, and you fly in here. If you're flying up here, you'll never get turbulence. They don't give a shit, right? Not from these clouds. You get turbulence because there's actual waves, but not from the clouds themselves. Don't carry a lot of weight. These are your 1,000,000-pound clouds down here. Okay. And as you keep going up, you can get above all of the clouds. This is the tropopause. I don't think we fly this high, but I might be wrong. I'm not a flyer. Pilot?
Why is the dew point line Yeah, why does it come back to the right? Like, why does the temperature increase?
Here?
Yeah, right there. Why does that happen?
The temperature structure of the atmosphere is very, very dependent on what's in the atmosphere. So at the surface, it's the abundance of CO2 and water vapor, which act as greenhouse gases to warm the surface. As you head up, you have other molecules, you have things like, if you go high enough, right? So like once the tropopause turns over, it becomes a thermopause, there's heating from ozone. So each of these different regions can have different heating sources depending on the microphysics. Sometimes there's like a little, you move up and it starts to cool down after all the clouds form. And then it warms back up again. And you're like, well, what the fuck is going on there? The vent flare. Here is a version of what I like to show. So just showing the different ways that waves can propagate in the atmosphere, how easily. So for example, here is an object, like a mountain. And as wind moves over it, it can form these ripples. And once you've formed those ripples, just like we saw before, they're happening on an internally stratified media, which means that they're happening on something that has layers, and each of those layers press into the layer above it, but they're not necessarily mixing as they do that. So these waves, they form here, right? Flowing over this thing, but they press waves higher and higher and higher into the atmosphere. And like we saw before, when we had some version of this in the water, where the waves sort of tapered off as they went down, these waves can taper off as they go up. The boundary condition is very different though, right? The boundary condition is the atmosphere. That extends up and up and up until it disappears, so the density goes to zero. So it's not just that you have some waves that are propagating in the atmosphere. You can have them interact. So you can launch waves from here. They can interact in the middle atmosphere and even into the upper atmosphere. And waves can bounce off things like clouds. They can hit clouds and they can reflect off of them. They can bounce off of them.
Ocean,
Yeah.
is there an exact reason why it feels like the movement of like waves sort of is like opposite to that what's going on in the ocean?
What do you mean by that?
Like you said, like how the ocean is sort of like tapers off.
Oh, yeah.
But then in the atmosphere, it sort of tapers up.
Yeah. Good question. So
I want to say again, it has to do with the boundary conditions, because in the ocean, as you started waves on the top, you go all the way down, right? There's not, you don't, like the waves, they start to like get lower as you start to like reach more depth. And it's the same right here, where the waves start at the bottom and it starts to get, I guess, like lower as you get a higher altitude.
Well, the only thing I would say differently there is that the water and the air are two different mediums, right? So water is incompressible for the most part, what we were considering. This air is very compressible, right? So it certainly looks symmetric when we think about the boundary here and launching waves upwards. But what I was trying to think about was the fact that you can launch waves off of something like this. So if you have wind that comes in and hits an object, it launches waves in both directions. And they may propagate quite differently. Right?
So it's just
So it may just be, I don't want to say it's coincidence. I think it has to do with the fact that it's a wave interface, right? So where your wave is being created, you do get quite similar effects. That away from that, because there's viscosity, because there's abilities to sap the energy, that's why the perturbation gets smaller. And that's similar in both media. But whether or not they should have the same shape this way and this way, I think is maybe coincidental. Is that an okay explanation?
Yeah.
Okay, so let's go. Oh, here's my example. Sick, right? What do you see? No, look closer.
A dispersion waves.
The dispersion of waves. Which way is moving the fastest?
Already gone.
The one in the front. No, but what do you see about it?
Biggest one.
It's the biggest one, not just the amplitude and width. The width is the widest, right? It's here. You can't even see it, it's the biggest one. It's so wide, and then this one is less wide than this one. You see? Which one moves the fastest? It's the one with the longest wavelength. It didn't even lie today. Okay.
Yeah, some days I don't trust.
Hey, sometimes he's just making shit up from the book. Okay. All right, what's this one? What am I showing you?
Trick question.
What?
What's the trick question?
Yeah,
They're urging.
good.
One's at the north, one's at the south.
How do you know that?
I know there's a direction, but I don't know. There's a reason, right, with the rotation.
Mhm.
Oh, the Coriolis effect.
Yeah, so which one's which?
I'll take a guess, the left is the north.
I'm gonna go opposite of that, so that's just the south, actually.
Yeah.
50-50.
Cause what way does the water flow in the toilet when you flush?
No.
Oh,
Yeah,
I'm about to get.
1,076, man, they lied.
6 seconds.
Yeah, it's not straight, yeah, so.
Oh, no.
Oh man. Okay.
I'm using my knowledge.
It's good. I mean, it's good to draw on personal experience, right? But that's bad personal experience. Because unless you've gone to Australia, you would not be able to tell. And when I go to the restroom here, it just sucks it straight out. Right? So if you've ever looked at a toilet too closely, you can figure out why they rotate counterclockwise or clockwise. You know why that is? On one side is a place where the water comes out. And the water comes out like this, and then it spins around in a circle. There is not two jets, there's one jet, but the water comes out.
Right, 2 jets, what would that look like?
If you have two jets, the water would come out, splash, and go up your butt, and out of the toilet bowl.
And that would not be toilet
water
paper.
over there. You want it to spin around in a circle, because then you're taking all that stuff, you're getting it nice, and then it sucks into your little water bowl. What causes the toilet to drain?
It's the thing at the bottom.
At the bottom,
It's not going up, is it?
Well, it's like the pressure difference,
Yeah.
you add more water and it pushes the water in.
you guys have clearly not spent enough time on the pot, huh? Alright.
Study the toilet.
I'll study
You don't study the toilet?
You just use it.
No appreciation for the craft. Alright. You've seen this before? What's that?
I do the
Poo pee pee, right? Right? Okay. So this is, okay? Something like that. Okay, poo pee pee time. Ever seen that?
Oh, okay, I see that.
This is water. This is air. This is water. Why do we have this?
It's a creative factory or something, right?
Close. Create a trap. This is called your S trap or P trap, depending on what you have in your actual toilet. And what it does is it stops, say, methane and hydrosulfuric gas from your sewer, which can kill you, from moving through your toilet and up, bubbling through your water and making your house smell like shit. Okay, and also horrifying for you because it's like methane's very flammable, do that, right? So we put a little bubble, we have a little trap here. And we take advantage of the fact that if you have water, air, water, then it won't like permeate out through the air and then back through the other side. It traps it. So how does the toilet work? Well, you start with a low water level like this. All of a sudden, you add water very rapidly. You need to do it quickly. So that what happens is you start to pull this right over. So there's a little bit of space above the siphon. And once you get it over, then it pulls all of the water over. So you just need enough water to do it to here, right? So that you can suck it all of, and once it sucks all the way over, then it's empty again. And whatever water is left, it stops the siphon. Right? And slowly moves back up till these two are at the same level. That's a slow refill. So it's one giant refill and then two slow, then it's slow. Right?
So if I take a big enough pee, it should flush on its own.
That's exactly right. In fact, people have done this before. No one has actually peed that much. You don't pee enough. But that's the goal, is that you would want to do that experiment. Almost everyone's first natural question is, if I shit watery poop quickly enough, can I make the water flush? And you could.
Awesome.
Right? So that's how the flushing mechanism works. Look at it. That counts as class. Okay. I don't remember why we're talking about that, but that's not what this is. Yeah. So Coriolis forces, which are the forces that we encounter when we're thinking about planetary scale lengths. Due to the rotation of the Earth, flows don't move straight because the object under which they are moving is changing. So similarly, when you sit on a merry-go-round and you throw a ball to your friend, it doesn't go straight. Well, it goes straight to someone who's standing on the ground, but it appears to curve to you. So since we are all on this merry-go-round going around together, flows that appear to be moving straight to an alien in space would in fact seem to curve to us. Okay, so no context clues here.
So can you do that experiment, like, if you have a drone, like 100 feet in the air, and you're spinning somebody on a merry-go-round and throw a ball at you, can you see that curve?
What?
Thinking like, if I put you on a merry-go-round and you have a ball, and I spin you, you throw it to me, there's a drone like 100 feet in the air that like is looking down at us.
Yeah, you don't even need a drone.
Yeah.
It's on YouTube. You just sit two people on it and you roll the ball or you throw the ball. What happens is, instead of, let's say we're sitting across from each other and you're sitting to the left of us, I throw the ball to Trinity and the ball ends up with you. We can run this experiment in merry-go-round tonight. No drone necessary. But if you want to hire a drone, you can. Okay. Cool beans?
Which one's which?
Which one is which what?
Which one was
Oh yeah, the right is the north. The right is north, the left is south. This is in this one is in not Malaysia, Micronesia, what's it called?
Indonesia.
Indonesia. There you go. Okay. This is where we're headed. So we've seen this nice equation, right? What is this one? Everyone forgot already? Oh, good thing we don't have a homework or two on this. What's that?
Vorticity.
That's the vorticity equation, good. Is that it? What are these things? Yeah.
That's how you mess with the vortex lines, see if I can find a better explanation.
One's the like how it disperses, and the other one is how fast it moves.
Not quite.
So
Both words are so close. They
okay.
get like 90% credit. Tilting,
left one is tilting vorticity line. Right one's the diffusion.
Right, you said dispersal, diffusion is the word I would use. Same idea, right? Good. Okay, so this is where we're headed. Understand. Hurricanes, you need this. Oh boy, you can see a few things we know and love. That's our diffusion equation. This one here, you love this one. What?
Pressure gradient.
Pressure gradient. So pressure gradient for this one?
Body.
You two.
Gravity.
Gravity. Let's go. Okay, what is this one, this one, this one, and this one?
What's the primes?
Oh, relax. Okay, just chill.
This. Why is it friends? Why is it one?
What's this one? What's up?
Turtle chain.
What?
I wanna say velocity, but,
Yeah, but what is du dt?
Total change velocity. Over time.
Velocity over time is a.
Sorry.
Yeah, right? So this is the frame acceleration. If you are in a moving reference frame, then you introduce a force because the frame is moving. What's this one? I don't know, I wasn't paying attention. Okay, this is a rotations, right? We'll see each one of these. One of these is the Coriolis force, right? Okay. So let's talk, do we want to do this? Internal waves on a density interface? We do, right?
It kind of
Looks
looks like
like
that.
that.
one we talked-
What?
So it kind of looks like that one we talked about.
Yeah, so this is like, we talked about the difference between a fluid with nothing above it, right? But now let's have a look at this example, right? So we were talking about all these different types of clouds. In order to understand them, we need to understand stably stratified media. So what I mean by that is this has one density, rho one, this is density rho two, and rho two is greater than rho one. You can have a medium where rho one is less than rho two. And these are flipped around. Sorry, I should say this different. Well, rho two is less than rho one, right? What is the example when rho two is less than rho one down here, rho two, rho one up here? What is that called? That, any example you can think of where you have a lower dense medium below a higher density.
oil and water. Or.
Yeah,
it's
when
the
you have
opposite.
that, when you have that, correct.
Cookie.
Being in the kitchen is the right thought, but not oil and water. You're thinking about two different media. This is the same media with two different things happening. What?
Like freezing water.
Freezing is moving away from being solid.
So boiling.
Boiling. What happens with boiling water? You have hot water at the bottom, cold water at the top, and the hot water has a lower density, so it goes skyrocketing up. You do not get waves then, right? That would be an unstable configuration. This is a stable configuration because the heavier stuff is below the lighter stuff. So even though we get some perturbation, we move this light stuff down, there is a buoyant restoring force to bring it back up. Now, similarly, when I push this down and I move this fluid out of the way and it pushes up, now it's higher than it wants to be. And gravity acts as a restoring force to pull it back down. Right? So you can have waves on a density interface. An example of a density interface that is stable could be, for example, let's think just about water right now. Have you ever seen like salt inversions? Or like salt where sometimes you see them in really cool pictures of the Amazon. So this is the Amazon River and it's letting out like this. So Amazon River famously is a what type of river? What kind of water? Fresh water. This is fresh water. And fresh water means what about the water? No salt. No salt. Okay. So this is fresh water, and out here, this is called the ocean. And this has salt. All right, very good. Everyone's getting it. Okay. So you see these famous images where fresh water does this. And it's like dirty and murky. Okay. And there's very like freshwater fishes in it. And there's a actual line in the water, and the ocean is here. Okay. And the flow is coming out, and they don't want to mix. They move by each other. This is when seen from above. And when it's seen from the side, okay, you have this situation. Okay, the fresh that sits above salt. Why is the salt water below the fresh water? It's heavier, right? And if you love some of these like nature shows, there's always this great example of like you can I forget exactly where it is. You're like diving and you go down into these caves. And you move into these caves where these super, super dense salt regions are. And the water is so clear that you can see fine, right? You have your goggles on, everything's fine. And then you look at these little cave pools that are filled with salt water that can't get out, and they look like water underwater. You can see the density difference. And you can walk in them, right? You float in them. You can put something in them, and they float on that other media. So what's happening here is you have two media, one of which is floating on top of the other, and from which waves can propagate. Okay? So before we talked about waves, a single wave, right? We didn't consider what the media was above. But of course, when we were thinking about something like an ocean wave, or we were thinking about a lake wave, that's really two media, isn't it? It's one media up here that's air, and another media down here that's not. Okay. I don't know if I want to do this. It's a lot of math. I don't think you guys care. What? I mean, I just, here's the thing is I don't know if this is like, you guys love the wave equation stuff that we did earlier? And you're gonna do a really good homework on it, right? Once you finally do the homework? Okay. I'll just show you one picture, which I think is really important, and then we can move to, because I do want to get into the rotation. Okay. All right.
No question.
No such thing.
In space, if you just have like volume of water, you don't need this many equations, right? For like the other medium,
Excuse me?
like if you just had a ball of water in space, like you don't need. I don't understand, like, I think a lot of assumptions you make you don't need such intricate equations, right?
So you have a bottle of water. Is that what you're saying?
Ball.
Okay, you have a ball.
Yeah,
No gravity.
no, just chill.
Just chilling. And then what happens?
That's what I'm saying, like,
Surface tension.
but that would be it, right? You don't need all this other stuff.
Well, okay, so if you have just a ball of water, it's not as though it's not susceptible to gravity. It's not as though it's not susceptible to pressure. It's that the pressure is zero. The equation still applies. Just many of the terms are zero,
Right.
right? So for example, when we think about that really long one that we just introduced, right? That is still part of the best version of this equation. The only thing is that when we think about water in a pipe, we say, well, those terms are so small as to be negligible. Okay? And when we begin to ask questions about where can we use these equations versus others, right? Like a balance of gravity versus something else, right? You have to be able to say, well, this term won't be important. Like, for example, when we want to look at how is the atmosphere stratified, okay? How are the layers built? Then you might say to yourself, well, over that scale, the atmosphere has basically no viscosity. So let's throw away the viscosity terms. But those will always be choices. The true equation includes every single term. Okay. Let's see. Unfortunately, I do want to teach you the Brunt solid frequency. That means I do have to teach you about dispersion of waves. Okay. I'm just going to give you the highlights. How's that sound? Rather than work through it, you're going to believe me when I tell you these things. And they are in your book. This is chapter 8.7. And essentially what we would do here is just like we did before, where we assume that the free surface has some wave form. Remember that we said for the free surface eta, it was like A cosine, right? So we would do the same thing here. We would say, okay, these things, they share a boundary, and you would give them some exponential decay that moves up or down into the fluid, and they would have some sinusoidal x going left and right. Okay. You would get a dispersion relationship that looks like this. Omega is going to be GK rho 2 minus rho 1 over rho 2 plus rho 1. Okay. What happens if they're the same?
Zero.
It's zero. Because in a single fluid, there is no wave from a density interface. There's no density interface because the densities are the same. Now you can also imagine that this could be some stably stratified medium, many fluids on top of each other, launching waves back and forth, right? So we can increase this if we needed to for more than one type of wave form. We can sometimes write this like epsilon GK. Okay. And this boundary or this dispersion relationship, this is I just took this stuff and I turned it into this little epsilon. Okay. Generally speaking, 2 and 1, right? If 2 is bigger than 1, this is going to be positive. Is this number here bigger or less than 1? It's less than 1, right? This is really important because remember that we said C is equal to omega over K. So it turns out, right, that waves on a density interface, since this thing tends to be less than one, right? Must be, if the density interface is stable, they move slower than those that would exist if this was 0, right? If, well, let's do it the other way around. Yeah, row 1 was 0, 0, right? There's nothing out there. Those are gone, then that's 1. That fair? So the more close they are to comparable, the slower these waves propagate compared to their neighbors near the surface, where the density is close to 0. Okay? This leads to really cool shit. So, there's this cool picture in the book. It's called 8.26. I'll call that, sorry. The number in the book is 8.26, and it's called dead water. And you get your little boat, okay? And your boat's going to the right. So you have lighter fresh water that you're sort of going over. And this is traditionally what happens like near a fjord. So in a fjord, for example, the water is melting off the glacier. So it's kind of similar to this, right? Because you have some source of fresh water that's interacting with the ocean. And so fjords sometimes are these canals that are carved out by the retreating glacier, and they're melting directly and they create these rivers. What they do is they have fresh water that's yet to mix with the salt water. Salt water is sitting in there because it's the ocean level, and then this is sitting on top of it. And so you get this heavier salty water, so you have fresh above the salt. And the cool thing here is the perturber is the boat. The boat's moving left and right. As the boat launches a wave, it goes down into the medium, right? And it hits this density interface, and it goes like this. Right? Which is pretty sick. And this type of work, you can show how these density waves propagate down with Z. But it's like that. Okay, yeah.
So it's kind of exactly like those sonic booms in front of a jet. That's not how they would go down.
Yeah.
Okay.
No, and sonic booms require the worst version of fluid dynamics. Because what?
It's like blow up the boundary, right?
No, so sonic booms are a form of fluid dynamics called shock dynamics. And remember we had that cylinder, and it was able to communicate to its colleagues ahead of it that something was there. So that happens with a limited speed. The air can only move at a certain speed. If you're moving faster than that, then there is no way to communicate to your colleagues that there's something coming. And so therefore, instead of there being a continuous form of the fluid dynamics equations, you have discontinuities. And those are called shocks or shock boundaries, right? So the reason that you get a very specific shape in your sonic boom, so to speak, is due to the discontinuity in information being able to propagate between the two media. You may notice that I'm using the words communicate and information. These are the correct ways to think about it, right? Because information must travel, right? Like there is a boundary here, and that is something that the medium is telling to other parts of the medium. If it cannot communicate, then it cannot adjust, right? Have you ever seen this? You take a slinky, okay? You hold the slinky by one end, and then you let go with your hand. What happens to the slinky?
Like waits for it.
No, it moves down and close on top as it goes down.
Yes. So does the bottom start moving when you let go of the top? No. The bottom does not move. Why?
So they told it it's falling yet.
It hasn't been told that it's falling yet. It's communication. There is a wave that needs to propagate down the slinky that is relieving the tension that was holding it up. Things don't happen instantaneously in physics. They need to be communicated by force carriers, right? And just like your example with the shock wave, you need to communicate through force of collisions, right? And if that doesn't happen, you get a shock. Okay. I'm really not moving through this fast, even though we are skipping through the class. Okay, so oh god, this is the worst part, but I love this part of the text. So let's look at a version of these equations that is it's simple. Okay. We want to consider fluid on a continuously stratified media. And the reason why this is so important is we've made these approximations first, like what does the interface look like at the very top? And then arbitrarily two things of different densities, right? So now let's ask the real question. And the real question is what happens when the density is changing smoothly as a function of height, right? Because that's really what you tend to find, is that as you move up the mountain, it's not like you have, thin air at the top and thick air at the bottom. As you go up, slowly it's changing, right? Right, okay. So we're going to present something called the Boussinesq approximation, which is written like this. Boussinesq. This is probably French. I'm going to treat the density as constant, except in the vertical momentum equation. So it's constant in x and y, for example, but not in z. Except. Okay. We're also going to assume that the wave motion is inviscid. Okay. And amplitudes are large, or sorry, amplitudes are small. Such that advection can be ignored. And then finally, the frequency is small, or sorry, is much larger than the rotation of the Earth. So that Coriolis solar system operates. Okay. So this is pretty straightforward set of approximations. What this basically says is that the density at each vertical level is constant, but that it's changing vertically. It's homogeneous in this direction, but not this direction. This one says that the wave motion itself is reversible. You don't have viscosity here that is sapping away the energy as a function of the viscosity, right? This one here says that we're not yet caring about advection of the flow, right? The nonlinear forms like wave breaking, etc. So we will see turbulence, that includes wave breaking. And then finally here, we're going to say, let's ignore any Coriolis frame rotation. You don't yet have these terms, but you know in your mind's eye that they might exist, right? Okay. So this allows us to write something really nice. You're familiar with this? What's that?
Density. Volume.
Come on, guys, we've done this so many weeks now. What is it?
Say conservation.
Conservation of mass, and so therefore it's equal to. Good. That should be your first instinct. The only right answer. Okay. And the second one, this one's fun. Okay, let's break apart the u dx plus the v dy plus the w dz, and that's going to be 0 too. Okay. So this allows us to write some really fun stuff with the momentum equation, with the pressure equations, right? So we can say something like du dt is equal to 1 over, this is some density, right, at a location, dp dx. So that's like the pressure gradient terms. And then this is also quite similar to d v dt. Gonna have the same form. In fact, I might have not wrote it because that would have saved me some writing, but I did. So fuck, I know I have to do it. So the only one that's different is the z. And the reason that it's different is because we have gravity in the vertical direction, right? So let's write dw dt is equal to minus 1 over rho naught d p d oops z minus rho g over rho. Okay. So this is your Navier-Stokes equation. Super easy, right? We said that it's inviscid. So the only term that matters in the horizontal direction is pressure gradients, right? The change in the momentum is due only to pressure gradients in x. The change in the v momentum is only due to pressure gradients in y. The one that's different is the z momentum. And that is because it's moderated by differences in density. You'll notice that I wrote rho over rho naught. So if the density of the fluid is different than the density of its neighbors, then you go up or down. This is a buoyant force. Okay. And similarly, we can use all three of these to understand waves in this vertically stratified media. Now remember that stratification by definition means no mixing, it's layering. Stratification means layering, right? All the way down. So what we're going to look for is we're going to look at perturbations in that layering. Okay. Oh boy.
Did we say what omega was, or that's the same omega?
That's on omega, that's W.
So,
That's this W.
okay, what's that, what's like, we haven't said it.
This is the, sorry, this was the rotation of the Earth. This is saying you
Oh,
could ignore
okay.
the rotation of the Earth. Okay. So typically what we want to do when we do a problem like this is we want to look at what are the first order approximations and then what are the modifications to them. So the first thing that you might say here is if it's vertically stratified, what does it look like in hydrostatic balance? And by definition, hydrostatic balance would say that this term here is 0. So this would be 0 for hydro balance, right? Because by definition, that means that it's not moving. So what you could do quite easily then is to determine this equation. And you could say to yourself, let's write the pressure as the average pressure at a given location plus some perturbation. Okay, this is quite a standard way of doing physics. You take the first order approximation and you subtract it off and you look at the result of the perturbation. So similarly, you might see something like this, right? So you have rho, so average rho at the location plus the perturbation. Okay. And then you put this thing into here. Okay. So the density equation, which is here, can use both of these. And you get some really horrible stuff. I'm going to write it just to see how bad it is. ddt of the density, which now we're going to write this. Okay. Plus u dx of the density plus the density. Okay, so on and so forth. Okay? That all equals 0. So I do it for x, you do it for y, you do it for z. Everyone's happy, right? Okay. Now, for hydrostatic balance, we said things like d average dt must be 0. Right? So we said d rho average dt is equal to 0. But also what we said at the very beginning is that rho is constant horizontally. So let's also make that equal to d dx rho bar equals d dy rho bar, right? And that actually makes this a little bit easier. I'm just going to simplify this dramatically. Because now what we end up with is something like d rho prime dt plus w d rho bar dz equals. So what does this say? Well, this says something really fascinating. Okay, this says that the perturbation in density, right, that happens with respect to time is due to the vertical structure, the average vertical structure of the density. Questions?
The right side is vertical, what's the left side?
This thing here? Remember that this part here, these are perturbations from the density. So any perturbations that exist, right, they're characterized by flow and the vertical flow and the gradient of the density, average density, with respect to the vertical.
What do you mean these different?
So remember we started up here by saying, look, let's take the first order, right? The first order would say that this thing here was equal to 0. And from that, I could solve this equation for the other one. So I could get something like P as a function of height, right? And that would be this thing. So let's imagine, right? Let's take a fluid like the Earth's atmosphere. And let's say that it's in hydrostatic balance here. Okay, and it has some temperature that goes up, or sorry, that goes down as a function of height. Then the first order approximation for pressure and for density, these pieces here, is that they should be exponentials with the scale height. We saw this in like week 1, 2, right? That we can set these equal to each other. We can use the ideal gas law to replace P with rho, and then you have dP rho or dP dz equals P. And that by definition must be an exponential, right? So if you do that, then you solve the original sort of vertical stratification. And now the question is, if you start with that, but you add a little schmutz, how does that schmutz react in the equations, right? So start with your vertical density profile and just add a little something. You don't know what that something looks like yet, but we're about to see. Right? Okay, well, I'm going to show you anyway, and then we'll come back to this. So we're gonna need something here that we call the brunt Vaisala frequency. Oh my God, I'm gonna do the wrong number of dots. Yeah, there's a shit ton of dots, okay? This is the brunt Vaisala frequency, and it works like n squared equals minus g over rho naught d dz of this thing rho r. And this essentially is a wave propagation criterion. So we will see in the next time that we talk about this on Monday, we will use this in order to determine whether a fluid is stable or unstable to convection. That is to say, if you create a wave, does it just propagate up and down with buoyancy being the restoring force? Or does it go and it fly away? So if, for example, you have something like the fluid that we were talking about at the very beginning, such as boiling water, right? If you heat up the water too much, it doesn't come back down. It goes up and it stays up. Right? That is not a wave, that is convection. That's a completely different process. And the criterion for convection is hidden right here, brunt Vaisala frequency. The description of the vertical structure here. And because this is a frequency, you're going to end up seeing it in a wave. And if this thing becomes negative, you'll see in the wave that then the wave becomes not sinusoidal, but an exponential, right? Okay. So that's the fun thing. We'll talk about it. I guess on Monday. It's sad that you don't get to talk about that. What else? Any questions, comments, concerns? Homeworks? Show me what you got. Well, show me what you got, what you really got. Yeah, because once we finish this, then we can talk about rotation, planetary rotation. And I think